All right, so it's time for an update on the GPS disciplined oscillator. Where we last left off, I had the LEDs that are showing the relationship between the 10 megahertz clock and the PPS signal from the GPS. And so shown here, if the PPS happens, the clock edge occurs midway through the next cycle. And then this clock is running a bit fast, so that edge, which is right here, is inching slowly towards the time when the PPS comes. So if it's running fast, I know I need to slow it down by adding 1 to the DAC control word. And what I wanted to do is I wanted to have the processor read this out and then display it graphically on the LCD display, which is shown here. And so, here E1 is that's a E, that's a 1. That's the value that is read back by the processor. There's a C3, that's C, that's 3. And then shown here is a representation of the LEDs. And so for each character position, I'm showing 2 bits. And so here it's a 1 and 3. There's 1 and there's 3. And if it changes again, it's 3 on this side, 3 on that side. And I have a half line here to denote the left and right margins. And so this is an exact representation of the LEDs. And as you see it kind of move around, you see it matches. There's 3, there's 4, and there's a blank spot there, there's a blank spot there. And so it matches. And I'm going to get rid of having this display that's showing the real readback value and just rely on the graphical representation. I'll have some other data to put there. But I used this when I was debugging the system to make sure that what was shown here was actually being read back correctly, and then what was shown here was displayed correctly. And so the way I did this, this is the character map for the LCD driver chip, and it has a bunch of undefined characters. Each character in memory is a 8x8 grid of bits, so you can specify the image of the character, although in reality it's really a 5 wide by 8 high. It's actually displayed, because if you look at the display, there are blank spots between each 5 by 8 grid of bits. And then the bottom row is actually where the cursor goes. So, there's the cursor right there, and none of these characters use the bottom. And so to make your own characters, you just have to assign a bitmap, and then you can load that into one of these character positions. And then when you want to display it, you just tell the display to write whatever value is stored in that display position. So what I did is I made a set of bitmaps for each of the characters. And so, this is the left margin, right margin, left margin with an off and an on LED, right margin with an on and an off, 2 on LEDs, a blank, and then a left and a right LED on. And I initially was going to have, just because I didn't know how the display would look, I was going to have just sort of a line if there wasn't any data to be shown, so you sort of see where the dividing lines are, so you can figure out where the bit positions are. But actually on the display, since each character, even when it's blank, it stands out from the other ones because there's this light patch between them. You know how it's lined up. So I decided to delete those. And then to actually make the character, you just have to read out the bits. And so since it's an 8x8 array, there's really three zeros here, and then there's the actual character. That's why the character here is a 1 and a 0, because that's 1, that's 0. This is a 1 and a 3, it's a 1, that's a 3. This is a 0 and a 6, because, this is a 1 and an 8, because there's the 1, there's the 8, the leading digits are 0. So for each of the, clock edge positions, I kind of, did a test where I drew out what what characters, so 04 is the character which corresponds to this. And so for each of these 8 clock positions, I drew out what the character is going to be. And so I made a program that every second it just sort of walked this clock edge pattern along. And that's how I verified that I like the way the display works. I was able to just sort of tweak it by getting rid of these reference blank marks. So then to actually figure out what to display for the actual value, if you remember that this value here is what's being read out by the I/O expander. So 7, 8, that's a 7 and that's an 8. To actually display these characters, I take the phase comparator value, which is 8 bits, and I have I write 4 characters. So this is the first, second, third, and fourth character going across, and so I take the phase comparator value and I and it with C0, which leaves me with basically the upper 2 bits, and so here are the 4 combinations of those upper 2 bits, and then those correspond to the character that I put in there. So if it's a 8-0, which means that there's only a bit on the far left-hand side, it's character 6, and character 6 is that. If there are no bits present, I write character 0, and character 0 is the left-hand margin. And so I do that for the 2 bits in the first character. These are the 2 bits in the second character. These are the 2 bits for in the third character, and these are the 2 bits I use to generate the fourth character. And so I have a lookup table, and I write the 4 characters depending on what the 2 bits are. So then if you, again, look at this, here's a character. It has 2 bits. So right now I'm writing character 1. As the bits, march over, I write a different character in that position. So it's pretty straightforward. The software actually wants to know where the edge is, and so that this value up here is where the edge is. So I've numbered each of these bits. This is bit 0, 1, 2, 3, 4, 5, 6, 7. And so so here it's at 6, the leading edge is at 6. And now it's at 5. And so this basically corresponds to the relative phase of the 10 megahertz clock in relationship to the PPS signal. And that's really what the software is going to look at. And so there you see a jitter, PPS jitter event that happened, which happens when it's a 0, 0, 0, 1, 1, 1, 1. And so the software actually wants the leading edge to be actually at 0, so you avoid that. But so then if I need to know how I'm doing with that edge walking over, I just have to look at this phase comparator offset value. I don't have to look at that value. A human would want to look at this, and so when the edges are walking that way, it's going too slow. You need to speed things up. When the edge is walking that way, you need to slow it down, because again, this is time. So if these edges are creeping forward, that means there's more of them are occurring earlier and earlier because they're actually coming faster. And by the way, I'm happy with, it's going, almost a minute and just kind of sitting here without slipping an edge. But and of course now I'm in danger of doing the jog, which it just did, or the jitter. So that all works out well. I'm going to do some software work where I don't need that value anymore. I don't really know why I need what the count values are. That is useful for debugging. So I might try to simplify the display a little bit. And then also thinking about automating the tuning process, because I can always, I'm always tempted. I want to just flip it over to automatic tuning and have it go. So I might have to display, am I in coarse, wide, coarse, fine, whatever tuning mode, and so I'll need more room to have data as I'm debugging my algorithm. One thing I was going to do, which I might still do just as a waste of time exercise, was I wanted to instead of having 0 through 7 being the phase offset, actually really measure it in an analog kind of a way. And so I thought of a circuit that did that, which is this. This circuit generates a pulse, which is defined by the overlap or the time between the PPS coming and the next clock edge. So I'll see what I want to do. When the PPS comes, I want to have a pulse that goes from the instant the PPS comes until the 10 megahertz clock comes, and that the width of that pulse will be, in nanoseconds, the phase offset that's happening. And so there's a clever way to do that, which is to use D flip-flops. So a D flip-flop, when a clock edge occurs here, whatever value is at the D goes to the Q. And so the way the circuit works is if a PPS edge comes, I load the D always with a 1. So when the edge comes, the Q goes high. So edge comes, Q goes high. Then what I want to happen is I want the Q to go down when the 10 megahertz clock comes. And the way I can do that is I can have the 10 megahertz clock coming in here, and normally, normally Q is 0 and Q bar is 1, so that's 1 coming in here. So every time a 10 megahertz clock comes in before the PPS arrives, the data going out to the Q is a 1, and that 1 goes to the asynchronous reset of this flip-flop. And this reset is active low, so this means that since it's high, this flip-flop will not be reset. It'll retain its value. And currently the PPS hasn't come in yet. This has been reset, so the Q is 0. When the PPS comes, the data goes from D to Q. It goes high, which means that the Q goes from high to low. Since the D is low, the previous one was high, so the Q is high. But when the 10 megahertz clock comes along, it makes the Q of this bottom flip-flop go low, which actually resets the top flip-flop. When this top flip-flop gets reset, then the Q again goes low, Q bar goes high, and then the reset is deactivated, waiting for the PPS to come along. So PPS happens, Q goes on, Q bar gets clocked in at the next 10 megahertz clock, which is then used to reset this top flip-flop. And so you get a pulse width that corresponds to basically the time between the PPS and the 10 megahertz clock plus the time it takes to clear the reset. And so I wired this up, and basically it takes 15 nanoseconds to clear the reset. So the pulse width, normally the difference between these would be between 0 and 100 nanoseconds. Since I have the reset time in there, the pulse width is between 15 nanoseconds and 115 nanoseconds. And that will have a jitter to it, and it'll also grow or shrink depending on what the actual offset is. And so if I look at my display here, what I'm actually measuring is the distance between this LED and the first lit one, not a position of the edge. So what I wanted to do was then take this pulse, and I can fire it into a capacitor with constant current, which will change its voltage depending on how long it's on. And then I can combine, I can measure the voltage, and then I can short out the capacitor, reset it to 0, and wait for the next pulse to come in, feeding it constant current to charge up the cap, so I can measure the voltage again. And that would give me a time value, to the 10th of a nanosecond, I guess, of what that offset is. But there's a lot of jitter in the PPS clock, and there's noise in the system. And I probably I'll do the circuit just for fun, but it's a distraction, because right now, even though this edge it is jittering back and forth. The granularity, I'm looking at it with this circuit, doesn't show that jitter, and very rarely do you see an edge show up and disappear. It's always the steady march. And so, again, as an exercise, I want to do that just to say I've done it. But I see then there's a jittering again because of the PPS. But I don't want to have to worry about having filters in my measurement, because that's always going to be going back and forth. I like the fact that the granularity here is such that that jitter effect doesn't bother me, except when the edge is at position 5. So that's the current status. I'm waiting for the socket to come in so I can use my frequency generator chip. I mean, these are the chips in here, so you can see how tiny they are. I have 6 of them. There's no way I can solder it, so I need a socket to go there. I already have the 3.3 volt power supply. So then once it comes in, I'll wire that in. I have to hook up I2C. Have to level shift the I2C, I guess. Put the 10 megahertz in there and see how it goes. The challenge will be the software. There's multiple different filter and multiplier divide settings, and so I'm not sure how that's going to work. I might have just all the values on a screen, and you just have to just kind of type them in with up and down arrows, or I think initially I'll just have a fixed load that gets programmed in via I2C. Because for the frequency measurement test, you're going to kind of know what you want to set it to, and it won't take that long to just burn a new image into the processor. But I'm not sure long term how I can enter in lots of numbers that are 32 bits. So that's something I need to think about, because I'm not really thinking too far ahead on this project. I'm always doing the next micro step. So the next micro step here is to probably get rid of the LEDs, clean up the display, maybe make the software more structured. I probably I'm getting a B- on my coding practices. Like I have a lot of global variables and functions that don't return any values. So I would, computer science teacher would not like that. But again, happy with the performance. Maybe one of these days I'll hook up the 10 megahertz into the radio and see. I need to look at that also. So lots of stuff to do. Hopefully next week I'll get that socket. So I'll be able to start actually, and here's the chip that fell out. So you can see how absolutely tiny it is, and you can see or not see, depending on the focus, how small those pads are, and there's nothing visible from the top. So it is tiny chip. So that's the current progress. Thanks for watching. Until next time.